Hi, so today in this video we're going to be covering chapter 5.1, which is exponential functions and their graphs. So let's just hop right into it. There are a few things that we want to know when we are thinking of an exponential function. Our parent graph, let me just put this here. Our parent graph is going to look something like this. A to like C to the X. I don't remember the actual words that they use, the actual variables that they use. So this C will typically be something like a 2 or a 3, and this A is something that we multiply with. You don't need to worry about this yet, per se. But if we have something like f of x equals 2x, what that will look like is something like this. Let's make a little chart. So if x equals 0, anything to the 0th power equals 1. If x equals 1, then that will turn into 2. If x equals 2, that will turn into 4, and so on. We're just doing the powers. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We are always, unless there are different transformations, going to start at 0, 1, right here. And then we'll go up. We'll do 1, 2, and then 2, 4. Now let's say we did something like -1. If we did -1 for x, that would turn into 1/2, if you remember exponent rules. So we'll be like right here, sort of. And if you went on forever, you would notice a pattern that you can never reach 0 or negative numbers. So we have an asymptote at 0, at y equals 0. Let's throw some extra things into the loop. Say you had something like 2 to the x plus 3. In that case, what we're going to do is we're going to move our parent graph up by 3. So 1, 2, 3, 1, 2, 3, and this one would be like about right here. And our horizontal asymptote will also move up. So we'll do plus equals positive 3. So we cannot cross positive 3. Below positive 3. Now let's add an extra thing into the loop. So this is like our typical functions that we've seen before. But what if you had something like 2x minus 2? In that case, what would be happening is it's almost exactly the same as our quadratic equations. We're shifting over to the right by 2. We're switching these signs here. So 1, 2. 1, 1, 2. And our horizontal asymptote will not change. And then 1, 2. 1, 2. So our graph is going to look like this. And then what if you did plus 2? Then it would be going over to the side 2. I believe those are the horizontal changes, our shifts that we've learned. I'm not sure actually if this chapter deals with them, but it's good to know for next chapter. Maybe I'll just combine the two. No, I'll do a separate one. But these shifts are good to know. We're just sort of looking at this. So there are some things. Oh, and then what if we had something like 2x, but it'd be like 2 times 2x? This is the same. We're stretching, right? So what we're going to, and we're going to change this to green, at 1, well, when x equals 0, we're actually going up to 2. Because we're timesing our y by 2, basically, right? We're stretching up by 2. When x equals -1, this turns into 1/2, which turns into 1. So we're sort of like here now. And then if x equals 2, we're going to stretch again. So this will turn into 4 instead. I mean, sorry, if x equals 1, it will turn into 4. So here, and then, excuse me, if it was 2, then it would turn into 16 because we have, no, sorry. So if it was 2, then we have 4. and then 4 times 2 is 8. So then it would go up like this. So it's basically stretching our graph, our parent graph here. And then conversely, if it was a fraction multiplying, it would be compressing it. Those are the main transformations we've learned so far. I'm not sure if we've dealt with reflections yet. I believe it should be negative this. Anyway, going on to this. Oh, no, not yet. There are a few things to note. So if you had something like 2 times 2x, or like 4, let's do a different number, 3 times 2x. This 3 right here, this actually is what our book calls our initial value. It's basically just saying, and the reason why it says that is because like at 0, when x equals 0, our initial value is going to be like, our y is going to equal, in this case it'd be 3. And then the second term is the exponential growth pattern. This 2x, specifically this 2, is our exponential growth pattern. Let me see if there's any other language. I remember there is one more, but I'm not sure if they talk about it. Exponential growth pattern, initial value. There's one more. I'll put it in the comments when I figure it out, or it's just in my notes. Anyway, I don't think it's in this chapter though. If we come across it, I'll be like, oh, that's what I meant. Anyway, so what we want to do for this first problem is to complete a table for an exponential pattern of growth. The growth has a multiplication pattern of 4 and an initial value of 2. Then write an equation for the exponential growth patterns. Express your answers using either integers or fractions in lowest terms. Express the pattern in the form y equals a times bx. So what we're basically doing, we know that the multiplication pattern, okay, yeah, exponential, sorry, it wasn't the exponent that does it. The multiplication pattern is going to be this 3 here. In this case, it says it's 4. Oh, no, sorry. Multiplication pattern is the base, not the 3. So it would be the 2 in this case. My bad, I misspoke. So our multiplication pattern is 4. Our initial value is 2, and we'll have an x in the exponent. So if we plugged in negative 3 for this, we would have 4 to the negative 3, which is the same as 1 over 64, and then times 2, which is 1 over 32 when we reduce. So 1 over 32. Negative 2 is going to be 2 times 1 over 4. And that is, 1 over 16. Sorry, it's kind of late. 1 over 16, and that will turn into 1 over 8. Negative 1 is going to be 2 times 1 over 4, which is going to turn into 1/2. 0 is going to be 2 times 1, so 2. 1 is going to be 2 times 4, so 8. And 2 is going to be 2 times 16, yeah. Which is 32. So this would be your thing. And if you notice, there's kind of a pattern here. Here's a 1/2, here's a 2, here's a 1/8, here's an 8, here's a 32, and the 32. It's just a little bit, it's like, as one side gets smaller, the other side like kind of takes it. And then the pattern. So I know up to this point we've been saying it's f of x equals. For some reason they decide to just change back to y. So in this case it's going to be y equals 2 times 4x to the x power. I'm not sure why they decided to change. And I'm not sure why it marks you wrong if you do f of x. I'm not sure if it still does that or not, but it's kind of weird. This one we want to find equations for all of these. So we'll do y equals, our growth pattern is 5. Our growth is 5, so we'll do 5x, and our initial value is 5, so we'll do 5 times 5x. Our growth pattern for this one is 2, so that's our base, and then to the x, and then initial value is 4, so 4 times 2 to the x. Our growth pattern is 8 here, so for 8x, our initial value is 7, so 7 times 8x. Our growth pattern here is 4.25, so 4.25x times 2, And yeah, that covers that equation. Now we're talking about graphing. So let's fill in this box first. We have 3x. We don't have an initial initial multiplication value. Initial value, that's what they say. My bad. So we're just going to we can plug things in. So when this equals -3, we have 3 to the -3, which turns into 1 to the 3 over 3, which turns into 1 over 27. So 1 over 27. The 2 turns into 3 to the -2, 1 to the 1 over 9. 1 over 3, 1, 3, 9. And then to graph, this one right here is going to be our exponential growth. It looks sort of like, I don't know what it looks like. Yeah, I don't know, you decide. Like a wave or something. So we're not using linear and we're not doing a quadratic one, we're doing this. And so we'll plot one at 0, 1. Our y-intercept will be 1 if there are no transformations. And then at 1, we'll go up to 3. And then at -1, we'll do, well, actually, at this point, I don't believe that you would need to plot another point. I think it should just connect it for you. Sometimes it's a little weird, but you shouldn't need to plot another. It should connect it for you. This one has a fraction, so we're doing fill in the table of values for the function f of x equals 1/2 to the x. I cut that off accidentally. Express your answer as integers or fractions in the lowest terms. So this one's a little bit trickier. If it's a fraction, then it's going to flip our graph upside down. Well, not upside down. It's gonna reflect it across here. I'm pretty sure. It'll look like, instead of this, it will look like this. Yeah. So it doesn't flip upside down. It flips it side to side. So what our 0 is always going to still be 1, because anything to the 0th power equals 1. So 0 equals 1. And then at 1, 1/2 to the 1 power is just 1/2, right? So it's going to be right here. What we're more interested in, so 1/2. And this will turn into 1/4, because you have 1/2 times 1/2, which is 1/4. What I prefer looking at is the negative side of things, because that's where we're going to be getting whole numbers and not fractions. So if we're at -1, it will be 1/2 to the -1, which will turn it into 2 over 1, which is just 2, right? And so we're basically taking, it's just reversed now. So this will turn into 4 and this will turn into 8. So it'll look like this. Bloom. Keep in mind we still never touched 0. Graph the exponential function f of x equals 4 to the x. This one, it's the same type of principle. We always start at 1, then we go to 1, and then up 4. It's like we are over 1, up our base. And then, bloom, there's no crazy transformations that we need to worry about. So we can just do this. Determine the domain of f. Express your answer in interval notation. Now, it looks like it's going on forever this way, and it looks like it's going on forever this way, right? Like if we zoomed out and continue our graph, it would always go forever. It looks like it's always going up, but it doesn't really look like it's always going down, and we know that it can't cross 0, right? Nothing you can have is a negative or 0 for your answer if it's to an exponent. Like no exponent that you have can equal that. So our domain is always going to be negative infinity to positive infinity. Our range, however, is going to be different. Typically, if there are no transformations, you'll have 0, not included because it never touches 0, to positive infinity. And then the horizontal asymptote is going to be y equals 0. Now we're doing y now because it's horizontal. It's side to side. Vertical is up and down, right? Yeah, if you have any questions, please let me know and I'll answer as soon as possible. Sorry for being a bit later with this video.